Okay. So, now I think you are conversant with both the discrete model and the continuous model, means you have seen both of it. Now, I will use the continuous model to talk about superlinear and sublinear, means not superlinear sublinear per se, I will talk about a model which will encompass all the superlinear, sublinear, linear, all the various paradigms together. So, let us try to write the rate equation again in a very simplified way. Instead of kT, pk, I write nk. Okay? And this is basically what is happening, k minus 1 nodes, means this is the attachment rule, say attachment probability. Okay. And this is entering, this is exiting, and there is a sorry there is a spike function. Okay. So, what we have, this spike function is equal to 1 when k is equal to 1. Okay. At k is equal to 1, okay, we think m is equal to 1 here. Okay. Let us think m is equal to 1, that it joins with one node. Okay. And 0 otherwise. Okay. See why? Because at k is equal to 1, if m is equal to 1, at k is equal to 1, what is happening? Only one node is joining and this number of nodes are leaving. At other points is, see, at k is equal to 1, there is no a k minus 1. A is the attachment probability, like last time we said a k is proportional to k, or it can be proportional to k to the power minus count. Huh? A inverse is the normalizing constant. So, A inverse, A is equal to, A inverse is equal to summation 1 by, or yeah. So, A is equal to summation of kpk or something like this, we can think, summation of ki's. Okay. You have to have a normalizing constant. Sorry. I hope this part is clear. See what is happening? This is exiting, this is entering, this is exiting. At n is equal to 1, nothing is entering, only something is exiting, and what is entering? Just the node which is coming. The node which is coming has degree what? 1. So, that node. Okay. Enter, exit, at k is equal to 1, no, nothing enters, but what enters is the node which is coming in. Okay. So, the previous, in the all the previous cases we were writing two equation, now we have written a single equation. Okay. We were writing two equations at m k greater than m and k is equal to m. Similarly, we have written one equation. Okay. So, first I will go step by step. So, first let us, using this equation, can we calculate the moments? Say I say m and t, which is basically summation of j greater than 1 j to the power n n j t. I want to calculate the moments of this degree distribution. Okay. Just evaluating this degree distribution would be difficult. So, one way of thinking that I know the moments, first moment, second moment, third moment, fourth moment, and I can perhaps reconstruct the distribution from the moments. Okay. This is one way of thinking. So, let us think that can we calculate m0 t. from this equation. Okay. What is m0 t? Tell me. It is j to the power 0 n j t. Okay. So, this is basically n j t summation of n j t. Okay. Am I with you? Because j is equal to 0, here it was n, now here n is equal to 0, so j to the power 0, so j to the power 0 is anything to the power 0 is 1, so I have this. Agreed? Okay. So, now instead of m02, let us try to find out the sorry. Okay. Okay. So, this is equal to d dt of n0 t plus n1 t plus nk t. Okay. So, now write. So, n0 is not there, there is n1. Okay. Write. What can you write? So, as you go on adding, see everything goes. Okay, n1 t is 1, this 1 comes, plus this plus does not come, only minus comes, minus a1 n1 by a. Okay. n2 t. Okay, write n2 t. What is n2 t? Plus a1 n1 by a minus a2 n2 by a. Okay. Am I with you? So, if this goes on, there will be a plus minus, everything will be. So, what remains? This 1 just remains. Okay. So, then m0 okay. So, m0 t dot is equal to 1. Okay. Now, just I do the integration both side from 0 to t, 0 to t. Okay, I can do the integration both sides 0 to t, and what will this become? m0 t minus m00 is equal to t minus 0, because integration of 1 see. Agreed? m0 is a function of t, that is why m dot was there, no. So, difference I just integrate. This is dd, see this is actually d dt so this way. Okay. So, m0 t first moment is m00 plus t. Okay. Agreed? Okay. Let us try to find out m1 t. What is m1 t? d n j t summation. Okay. So, So, let me write the equations once more. Okay. What is the equation? That d n k dt is equal to A inverse A k minus 1 n k minus 1 minus A k n k plus okay. Okay. So, now see what happens. I again take the m1 dot t is equal to then d dt j into n j t, summation stays. So, the summation may come out okay, for all j's. Agreed? Okay. So, now let us try to write. I try to write 1 into 1 plus okay, 1 plus a 1 minus a 1 n 1 okay, plus 2 into a 1 n 1 minus a 2 n 2 okay, plus 3 into a 2 n 2 minus a 3 n 3 okay. Okay. So, what does this become? Tell me. 1 plus huh? Oh, 1 by a is there, sorry, yeah, I forgot. There is a 1 by a factor surely. Okay. There is a 1 by a factor, except for this 1 there is a 1 by a factor. And what is this a 1 n 1 a 2 n 2 by a? Huh? 1. So, this becomes 2. You understood why this becomes 1? Huh? Because this part is a is the normalizing constant and this part is basically a is what? Summation of a I a j n j okay. So, this becomes 1. I hope I am clear. Okay. So, then m 1 dot t is equal to 2 okay, and m 1 t is equal to m 0 t plus 2 t okay, and m 0 t again will be, you will see the, m 0 0. So, when the t is what t is the network size also okay, and 0 means no network size okay, no network okay. So, that is why m 1 t is equal to 2 t okay. Okay. So, let us sum up what we have now. m0 t is equal to m0 0 plus t, or and m1 t is equal to 2t. Okay. Okay. Now, what is a k? A, yeah, we do not, I am not sure, will come when it is needed. Okay. Since I did not prove it, I did not write that whether m00 is equal to 0. Okay. Because network size is 0. Okay. Actually, m00 is also 0. Okay. Okay. So, what is a k is equal to k? Let us think of a k is equal to k means is the linear model. Okay. If a k is equal to k, then m1 t is equal to a t. What is m1 t? Tell me. Is equal to summation of j n j. Okay. And what is a t? Tell me. Is means what is a? Means a t means I have just written in terms of t. A is means the normalizing constant. Okay, normalizing. It is what? Summation of a j n j. We know this. And what is a j? Is k or j, whatever you say. So this is equal to. Okay, accepted that a t is equal to m1 t. Okay. So now let us again revisit the equation d n k dt is equal to a inverse a k minus 1 n k minus 1 minus a k n k plus sum. So now a inverse, what does this become? 1 by 2 t. Okay. Because m1 t is 2 t. So the equation now can be written like this. Okay, clear? Okay. So now let us, what is our objective? What is our exactly objective? Finding n k for all k's. That would be the objective, that ultimately what are we trying to achieve? Degree distribution, that means n k. Okay. So in order to do this n k, the bottleneck which I told is solving this equation is difficult. Okay. So let us solve it for n1. Okay. So now what we will think, I will solve it for n1, n2, n3 and see whether the some generalization comes. Okay. We will try to see whether some generalization comes. Okay. So what is dn1 now? It is 1 by 2 t a0. So k is equal to a0 n0 minus a1 n1 plus, oh this does not come, huh? This is 0 and this 1 comes. Okay. And a1 is 1 because I have told a k is proportional to k. So this becomes 1 by 2 t minus 1 into n1 plus 1. Okay. So this is dn1 dt is equal to plus n1 by 2t is equal to 1. Are you accepting this? Naresh, are you accepting this? So, what is this basically? This is a differential equation, and if I solve this differential equation, I will get n1. Okay. So, how to solve this differential equation? How to solve this differential equation? Oh, great. So, multiply by e to the power this one, huh? E to the power half t dt, huh? Oh, sorry, this way also it will come. Okay. And what does this become? E to the power half t dt is e to the power log t to the power half dn dt plus n1 2t, and e to the power log t to the power half is why t square by 2 t to the power half. Yeah, 1 by 2 t I did. Yeah, it is 1 by 2 t. Don't sorry. Okay, it is 1 by 2 t. Otherwise, because I have to take this part as the integral, if you remember. Okay. Okay, and what is this part? d dt of n into so I can put d n, okay, this is I know t to the power half, I just put it. So, this becomes n t to the power half, and this becomes 2 by 3 t to the power 3 by 2, and n become n1 means it is all n1, I am n1 becomes 2 by 3 t. Okay. 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 So next thing what we see is I can do it, but n2 will become t by 6. Okay, same way you can go on doing. Okay, and n2 will become t by 6. So n what, and if you go on doing this, what you see is that nkt follows this formula.
Integration constant.
Yeah, there are integration constant, but you can take suitable thing and you can show that it comes. Again, if it is 0 to t, if you take it, this comes. Okay, same thing that m0 is 0 and okay. Am I with you? Okay, very good. So this is what we got. Then what should we do? Let us again go back to our old equation. What is our old equation? Okay, this is our old equation. So now nk is what? Tnk. Okay, so we have shown that nk scales to t. Okay, it's proportional to t. So now this part becomes just nk dt dt, which is equal to nk, which is equal to 1 by 2 k minus 1 is k minus 1. This is t nk minus 1 minus k tnk. Okay, I am just thinking that k greater than 1. Okay, if k greater than 1, then this part doesn't come. Agreed? So this becomes again k minus 1 nk minus 1 minus k nk. So nk becomes by 2, 2 is sorry. So nk becomes nk 1 plus k by 2 is equal to k minus 1 nk minus 1. Okay, so nk becomes k minus 1. Are you remembering something? Okay, so and you can also get n1 accordingly, and if you remember this, ultimately this recursion, if you solve this recursion equation, what will become? Nk equal to 4 by k plus 1 k plus 2, and that is what? What's that showing? K to the power minus 3. So it is proportional to the k to the power minus 3. The same old power law exponent of 3. So the beauty is that you can arrive at the same result through various models. Okay. 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 Now what happens is you can have a sublinear attachment. Okay, sublinear attachment, there are two assumptions. Okay, one is nk still k scales with t. Okay, it's still proportional to t. If it's a superlinear attachment, what will happen? Some nodes will get huge decrease, so it will not scale with t. Okay, but sublinear, we think that it's still proportional to t, and at instead of 2t, it will be mu t. Okay. Okay. So now again go back to our old equation. Now what is the old equation? Tnk dt is equal to 1 by, now I write mu t instead of 2t. Okay, a k minus 1 nk minus 1 minus A k n k. Okay. So, and what is this part? This part is again n k, just because I do this, I can do this n k d dt. Okay.
What is that is small n k?
This is a constant. This is a constant which is proportion. It's not constant. This is a function of k. It is independent of t, but it is a function of k. Okay. We have seen that, no, that for n is equal to 1, it was what? What was it? 2 by 3. N1 was 2 by 3. N2 was 1 by 6. So, a function goes on, and somehow we are trying to find that function, but the interesting thing is this function is independent of t. So, what was our basic assumption of this power law concept? Tell me, what was the basic idea? Basic idea was network grows, but the power of the degree distribution becomes independent of the growth. Okay. So, that is why it is a function surely, but that function is independent of t, the growth factor. Okay. So, now again you can put huh? Neta was that weight factor in the previous class. So, that is a completely different thing. Okay. Okay, I am sorry, I have to write this as T n k minus 1, and I completely messed this. Okay. So, 1 by mu t a k minus 1 t n k minus 1 minus a k t n k. Okay. And so, this becomes n k, I will do it in one step, n k 1 plus a k by mu is equal to a k minus 1 by mu n k minus 1. Okay. And so, n k becomes n k minus 1 a k minus 1 into mu plus a k. Okay. And n 1 we can do it, and we will find n 1 becomes 1 by mu. Okay. N 1 becomes ultimately, with all this you will see n 1 becomes mu plus a 1. Okay. So, what happens is, if you substitute suitably, you will get n k equals to mu by a j a k okay. Huh? N1 is equal to I just did this where I have this function, and I can find out. It will come, you can just check it, for n1 it will come, and so we get n k is equal to this function. So, what is unknown in this function? What is unknown in this function? Huh? Mu is unknown. We do not know mu, because we assume that mu t. Previously we knew the constant mu value, that was 2t. Now we have to find mu. Okay. So, let us again revisit and see what is A t. A t is equal to summation j and A t is equal to mu t. Okay. So, you put and n j is equal to t n j. Okay. So, put this mu t is equal to summation of A j t n j. Okay. So, mu is equal to summation of A j n j. Okay. Because t is goes, this t is goes. Okay. And what is n j or n k? I have written is as mu A j is equal to 1 to k 1 plus mu A j to the power minus 1. So, then mu is equal to summation A j mu by A j. So, this goes so mu everything begins to go, j is equal to 1 k 1 minus mu A j. So, essentially what you get, summation j is equal to 1 to k 1 minus mu A j. So, if you solve this, you can you know A j is some k to the power minus gamma. Okay. Then you can solve this and accordingly get mu. Huh? Yeah, here it was plus. Yeah, so it's plus, sure. Okay, it's little complicated, but the point which I want to drive is that you get mu. Okay, you can get the value of mu and accordingly solve it. You don't have to do these things. Once you have done, you can feed it to the computer and computer will do these things. So, we need not worry much. Okay, although it is complicated, what we are worried is the implication, because having a complicated equation always is defeating, because it is as good as the problem. Deciphering the equation which we get is as difficult as the problem which we have posed. That is always the problem with complicated equations. But anyway, luckily this can be suitably analyzed, and then what we see is that n k, okay, has this type of behavior. See, it's power law with the exponential cutoff. Okay. So, what is exponential cutoff? So, you have the power law here, say, and suddenly the higher degrees are tripped. Sorry. Suddenly the higher degrees are trimmed. So, you have the exponential cutoff. So, what is happening in a sublinear way? You have, first of all, this is less, this is smaller, because gamma is becoming small, gamma is no more 1. So, this is smaller, number 1. Number 2 is, what is happening is, you are not having high degree nodes. The high degree nodes are getting trimmed, and you see this happens at gamma is equal to 2, you get this, and then the first of all the exponent is becoming more flat. So, you will begin to have more flat things, and the exponential cutoff is also increasing. So, this will become more flat and this begins to shift, and this will go on for infinity. But there will be gamma is equal to 1/3, you will get exactly this equation. Then for gamma less than 1/3 to 1/4, okay, this way things goes on. Okay. So, there is a synchronous point. Gamma is a yeah, k to the power gamma. I took k to the power minus gamma, where gamma was, I told that this is a sublinear movement, because sublinear movement the assumption is T n k holds, n k is equal to T n k holds. Because if it is superlinear, what will happen, that some node will begin to have huge degrees. So then T n k, this T n k means some node will begin to have huge degrees as the network grows. Okay. So after some time you will get some Bill Gates, and you do not know what to do with him. Okay. So that happens. So it is not that the growth is uniform in some ways. Okay. So is this clear, sublinear part? Okay. So now, so superlinear thing, we come to the superlinear concept. I will not go into the mathematics too much, okay, because I think already it is heavy now. So first tell me what can happen in superlinear, which will not happen in linear. Like what has happened to Google? See, number of connection by a single node is almost is proportional to the total number of connections. So number of connections to a single node is proportional to the total number of connections. So if the network has infinite nodes, infinite edges, one single node also has infinite edge. Okay. So what is the worst model? Can you tell me? So I have nodes, each is coming with 1 degree. What is the worst model? Star. Okay. So then what happens is, one has degree n and all has degree 1. One has degree n, all has degree 1. Okay. So now tell me, I want to write the attachment probability. Okay. When a new node comes, and where I say it is proportional to k to the power gamma. Okay. When a new node comes, what is the attachment probability of what is its attachment probability of getting connected to this node? No, it is maybe almost 1, but I am trying to find it more methodically and more. So how many nodes are there? N. Okay. Problem name, there are n nodes. One node has n links. Okay, n minus 1 I know, but one node has n links. I am thinking n as large. All others have one link. Okay, this is clear. And what are we trying? Probability that a new node will get attached to the big node. So it is, this node has, so it is k. What is the summation? K summation k This is clear. This is the attachment probability, general attachment probability, that I have k to the power gamma, because it is not where gamma is greater than 1 by summation the normalizing constant. Now, for this it has, so n gamma, am I with you? This is n gamma, because this has n nodes, n links, so n gamma. Okay, n minus 1 is equal to n. Okay, we can always tell n minus 1, but for large system n minus 1, and all others have 1. So, 1 to the power gamma plus 1 to the power gamma plus 1 to the power gamma, this way goes on, plus n gamma. Huh? So, this is n to the power gamma, this is n plus n to the power. Agreed? Huh?
This will come down to 1 since n is large.
No, it will not come down to 1. So, this becomes, so phi becomes 1 if I divide 1 plus n to the power 1 minus gamma. If divide, I think n to the power gamma, n plus n to the power gamma, no, divide up and down by n to the power gamma. Okay. So, you get this. So, now see what is the probability that this will happen. See, this is an infinite process which is going on. So, what is the probability that this will continue for infinity? Is that think that when a single node is there is one, I join, second I join, third I join, fourth I join, I continuously is joining to the star node. Okay. So, and but it's a probabilistic joining. It's not that I am just seeing the star node and joining. I am probabilistically joining. So, if this continues forever, if this can this continue forever? This is the question which we are asking. Can this continue forever? If it has to continue forever, it has to be true for all these cases. So, all these probabilities has to be positive. And so, what happens is, am I making my case? So, this probability if it is equal to 0, then what we say? That this process cannot occur. But if this probability is finite, then we can say that this process can occur. If this probability is 0, we can immediately say that there is no chance, this will not happen. And who is controlling the probability in this equation? Gamma. Okay. Gamma is controlling the probability. So, we can show that if gamma is less than 2, then probability is equal to 0, while if gamma is greater than 2, then probability is finite. Okay. So, I will not do this is a series convergence problem, okay, which you can.
Actually, we have considered that n is very large, and we have make it and cancel out, and again in this equation we are putting from n is equal to 1, which won't be valid for a smaller thing.
No, we have not considered n is equal to very large. We may consider, but where have we used that? Yeah, n minus 1, it's large enough to consider n minus 1. Okay, you can change everything to n minus 1, it will not change much. Okay. It will not change much, it will not change the function completely. So, what we are trying to understand is the function. Okay. So, what is happening is at gamma greater than 2, When the exponent is greater than 2, you get gelation. Okay, you get gelation. That means you get a gel node or a star node. Okay, and this is how actually this theory is actually used how black holes are formed. Okay, so this is very similar to the theory used where how black holes are formed. Okay, you get gelation. Okay, okay. So now, which region still we have not explored? 1 to 2. Okay, gamma is equal to 1. So again, let us see what happens. I will try to write. Okay, so in this region, what we see, so what is happening is that first let us tell this question. What is happening? One node has infinite degree or huge degree or finite amount of or a portion of the entire network edges has been taken by one single node. Okay, and number of nodes having degree 1 is infinite. Number of nodes having degree 1 is infinite, or it grows. Number of nodes having degree 2, that does not grow. Okay, it does not grow infinitely. It grows maybe, but it does not grow infinitely. So now, if I see 2 to 3, the number of nodes with 2 links, this grows. Okay, this grows as t to the power 2 minus gamma. Okay, and while the number of nodes with more than 2 links is infinite. Okay. So there first case one link was infinite, number of nodes with one link is infinite, while number of nodes more than one link was finite. There was one single node which has degree n minus 1. Okay. So here 2 links is growing, number of nodes having 2 or less links is growing, while more than 2 links is finite. Okay. And then we can have again 4 by 3 into 2 by 3 by 2, where 3 links grows while number of nodes having more than 3 links is finite. Okay. So what will happen while gamma limit gamma tends to 1? Yeah, all the edges, all types of links will become infinite. Means there will be infinite number of 1 degree node, infinite number of 2 degree nodes, infinite number of 3 degree nodes. It will be infinite. Okay. So I hope we have covered enough this domain of preferential attachment, network growth, sublinear attachment, superlinear attachment, continuum model, discrete model, and I hope you will remember these things throughout your life. Okay, thank you.